Today we're going to do problem 1277, count square submatrices with all ones. Full disclosure, I haven't solved this problem yet, really haven't had an opportunity, been really busy. So we're just going to go through this problem kind of together, and then we'll see if a solution can be found. Okay, so you're given an m by n matrix of ones and zeros. Return how many square submatrices have all ones. It's kind of cool. This is the shortest problem description I've ever read. Okay, so I guess let's look at this example. So we have 0, 3 ones, 0, 3 ones, 4 ones, 3, 0, 3 ones. Okay. So within this system, right, we have 10 squares of side 1, or I'd say size 1. So we have this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, 10 ones, 10 size 1. Okay, and then let's look at size 2. So we have this one of size 2, and this one of size 2, and this one of size 2, and this one of size 2. Right, so there's 4 of size 2, and then there's 1 of size 3 here, right? So we get this green one. There's 1 of size 3. Okay. So this problem is very similar to another dynamic programming problem, which is find the maximum square in a system, right? And I think that I've already posted a video solution for that. So if you want to approach that problem before you approach this one, that would be a natural progression for this problem. And if I was in an interview situation and I was the interviewer, very likely if I wanted to ask multiple questions that were related, I'd first ask you to find the maximum square within a grid and then ask you to find the total number of squares that are in a grid, because they're very closely related. Like I'm instantly thinking of that problem when I'm solving this, and I'm going to use the intuition that I gained from that problem to solve this problem. And so how does that work? Well, we want to count all the squares. We don't want to overcount. And in order to count a square, you have to figure out what kind of square exists at a cell, right? So what I mean by that is it kind of relates to just finding the maximum square at a cell, right? Because when we look at this first cell here, the maximum square is size 1. So maybe what I'll do is I'll create this max square. We'll just call it square. Here, it'll be the same dimensions, and we'll save information about the maximum square that we've seen. Okay. So the maximum square here is 0, right? Because there's no square. The maximum square in this space is 1, meaning the maximum square where the bottom right edge. Okay, so I'm thinking about squares where the bottom right edge is in this position. There's 1 here, there's 1 here, there's 1 here, right? There's 1 here, there's 0 here, or there's 1 here, sorry. Here there's 2, right? Because there's a square where the bottom right edge is in this position, right? So there's 2 squares here. All right. There's 2 here as well, right? If we move over this thing, right, there's a 2 square here. There's a 0 and a 1 here. There's a square of size 2 in this position, right? And then there's a square of size 3 in this final position. So this is basically a system of the maximum squares that you can find where the bottom right of the square, right, the bottom right corner is in this position, right? So there's a square of size. Oh, I almost confused myself, by the way. I map this out, so it's just everything looks good here, right? Now, what I'm going to argue is that The number of squares total in the system is just the sum of this graph here, right? Because this one accounts for the one square that exists here, right? So let's go ahead and so this is gonna be a little messy, right? I'm gonna try something just to make a convincing argument. So there's a size 1 square here, a size 1 square here, a size 1 square here, a size 1, 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 a size 1. It's very inefficient what I'm doing right now, but I'm just trying to show you something to prove a point. There's a size 2 square here, a size 2 square here. Is that even, can you even see how that works? I don't know. It's a size 2 square here and a size 2 square here. And then there's the one size 3, not in red, let's do blue, and the one size 3 square. Okay, so I'm drawing all the squares. It's kind of messy in here, but I think that will make a little bit of sense as I pass this through. So this one here, what does that capture? Which square does that capture? Well, it captures the size 1 square that surrounds this node. Right? And likewise, you know, that's all for all the ones, right? All of the ones capture the one size squares in their nodes. So I'll just erase those, right? Like adding up this one accounts for this red square. So I'll erase it. Adding up this one accounts for this size 1 square. So I'll erase it. Right? Adding this one accounts for this size 1 square. Adding this one, this, so, you know. Okay. I knew this wasn't the best idea. Okay, now make sure I don't erase too many squares here. So there should be another green one right here. Okay. Right? So adding up all of the ones that I've highlighted so far accounts for all the red squares I've deleted, right? So I've counted all of these 1 squares. Now, what if I add this 2? Sorry, I deleted this one. Should not be deleted. All right, I haven't accounted for this one because I haven't added any square that ends in that corner. All right, so these are the remaining squares that I haven't accounted for. Well, if I add this 2, what does that account for? When I add this 2, what does that account for? Well, that would account for the size 2 square, right? So this square and the size 1 square that ends at that system, right? Because one way you can think of what we're doing here, right, is if I have a size, let's say 4 square, how many squares exist where this is the bottom? Well, there's the size 4 square, but in order for there to be a size 4 square, there has to be a size 3 square. In order for there to be a size 3 square, there has to be a size 2 square, right? In order for there to be a size 2 square, there has to be a size 1 square. So if the max square is size 4, right, that means that there's 4 squares that I can create where this is the bottom right corner, right? So when this is a 2, that means I am accounting for the 2 squares where this is the bottom right corner, right? So this S is really summing up all of the squares where the bottom right corners are in their positions. So this is 2, then those 2 get deleted, right? Since this is 2, then this and this get deleted. Right, because I'm just following the same process here. If I count this, then these 2 get deleted. And then something got deleted along the way, which is why this process isn't great. Right, so these would be the 3 remaining squares. Sorry, when I delete, I'm actually deleting. This would be the 3 remaining squares that I haven't accounted for yet. So then when I count this 3, well, then it's kind of like this system here, right? There's a 3 square. In order for there to be a 3 square, there's a 2 square. In order for there to be a 1 square, there's a, in order for there to be a 2 square, there's a 1 square, right? So I can just delete those. So I can just delete this, this, and this. And there you go. I've accounted for all the squares. So if I can just find the maximum squares that end in any corner, I can just find all those maximum squares and then just sum it at the end, and then I'll have the answer, right? And that's pretty efficient, right? Because, well, we don't know how efficient it is because we have to figure out what's the best way to find a max square. And I'll quickly review that. I suggest that you solve another problem, the other problem, which is finding the maximum before you do this. But the basic idea is if you have a position here, right? So you had a position X. What's the maximum square where the square ends in X, where the bottom right is X? Well, in order for there to be a square at x, how many positions to your left can you create a square? How many positions to your above you can you create a square? Right? And then what's the size of the square that's in this position x prime? Right? And the minimum of those three factors, right? The minimum of what's to my left, the minimum of what's above me, and the minimum of the square that is included is the resulting square that I can create. Right? So in this example, it's like, sorry, Max. Sorry, I have my dog with me. I don't know if you guys know this, but my dog is usually sitting with me when I solve these problems. Isn't that right, Maxime? Yeah, I love Leetcode. Leetcode's legit. Yeah. Alright, sorry. So that's the idea here. Oh, damn. Oh, your breath stinks, dude. Okay. Right, so like, for example, if you had something like this, right, if you had a system where it was... And let's assume that we've already run this process here. So here there would be a square here, right? And then to my left, I would say, okay, I have, 4 to my left and 3 here. So the maximum square I could create in this bottom position is the minimum of this system here, right? The minimum of this system to the left, and the size of this square. And the minimum is constrained by what's above me. So the maximum square I can create here is a 3 by 3. Right, so that's the basic idea for finding the maximum square that ends in a corner. So we can just run that process on each cell. And if we use a prefix sum idea of getting what's to my left and getting what's above me, and then just solve this problem so that, you solve this problem before you solve any problem that comes after, right? So imagine there was all ones here, right? If you've already solved what comes above, then from here you have the solution to solve what's below. And that's kind of a dynamic programming idea. Okay, so with that, let's go ahead and solve this problem. So we need to account for what's to the left of us and what's above us to figure out the maximum square that we can find, right? So we'll do that just using a prefix sum notion. So we'll do row. We'll copy each row for row in matrix. And we'll just do that twice so it's on the same line. So we're going to do this to find the maximum square in the system. So first we have to do this prefix sum idea. So we'll figure out how many how many elements are to the left, right? How many elements in a row are 1 to my left, right? Because that'll give us this idea of how many things are 1 to my left. So if I do for I in range, so I look at each row, and then for j in range, we start at 1 because there's nothing to the left of 0, right? So you can just start at 1. And then this is non-square. And then we'll say, okay, the left of I at j, if it's a 1, that's the only way that it could add in the previous thing. So if this is a 1, L of I at j plus equal L at I of j minus 1. And then we'll play this same game for above. But this goes in the other order because we're going to... That scares me when that's like that. Why is this over here? Oh, because I, for some reason, made a left when I should have made a right. Okay. Well, they know anything about Python, right? So now I'm going to check if things above me are true. So L of ij equals L of I minus 1 and j. And if this doesn't make sense, maybe I should just print it out, right? So if I print, if I look for L and L, and I print L, and I do for A in above, and I print above, maybe we'll print a little something here. So this isn't the solution or anything, right? I'm just trying to kind of show you the output so you see what I'm doing here. Oh, so I forgot to change this to A. I was wondering what was going on there. Right, because I need to figure out what's to my left, how many in a row to my left are ones, and how many in a row above me are ones. So does this make sense? So when it's 0, 1, 1, 1, I have, 0, so there's nothing to my left that I can consider to make me a 1 in a row. There's 1 in a row, 2 in a row, 3 in a row, right? Because there's 1 in a row, 2 in a row, 3 in a row. There's 1 in a row, 1 in a row, 2 in a row, 3 in a row, 4 in a row, 1 in a row, 2 in a row, 3 in a row, 4 in a row, 0 in a row, 1, 2, and 3, 0, 1, 2, 3. How about if we go from above, right? So there's 0, 1, 0. So 0, 1, 0. There should be 1 in a row. Okay, so I forgot to, right? So we look at each column. We don't need to look at the previous value, right? So that's why it's always good to debug if you can in an interview, because, we're kind of splitting up this problem into parts, right? Like we have to do a prefix sum part, and then we have to do a dynamic programming part. So let's see if we can solve the prefix sum part and ask, okay, can I just print this out to ensure that this is working before I continue to the next step? So always try to modularize your work. It's going to help you a lot. Okay, so I have 1 in a row, 2 in a row, 3 in a row, 1 in a row, 2 in a row, 3 in a row, 1 in a row, 2 in a row, 3 in a row, and that's what we see here, right? There's 1 in a row if we're going downwards, 2 in a row, 3 in a row, 1 in a row, 2 in a row, 3 in a row, right? So on and so forth. So from the left, this is the number that we have in a row here, and going downwards, there's this number in a row, right? Because this is 0, 1, 0, because, right, there's no kind of things happening in a row. 0, 1, 0. Okay, so now that we have this information, we can calculate at any cell how many to our left are 1 and how many above us are 1, right? Because if this is a 3 in the left, that means that there's 3 things, including myself, I guess, right? At this cell, there's 3 things, including myself, to my left in a row that are all 1s. And in this cell, there's 3 things above me, including myself, that are all 1s. So then now we just need to solve for the size of the square at any cell so that when I look at this information and this information, I can look at what's above, right? What's diagonal to me to see what size of a square can exist there, right? Because right now, essentially what we have is, if I have a 3 here, if this is left, right, and I'm just looking at, let's just say left was like this, and above was like this, right? What this is basically saying is like, okay, I know that there's a something in the system that looks like this, right? Since this is a 3 to my left, I know that there's 3 1s, including myself, to the left. And since this is a 3 above, I know I have 3 1s going up above, but I don't know, right? I don't know what's going on here, right? So since I don't know what's happening in this box, I can't make an assertion about the size of the largest square in this position. So instead, I'll just solve this problem for this cell, right? I'll solve the problem for this cell before I solve the problem for this square. So if this tells me that it's 2, well, then that means I know there's a 2 square here, and then I can draw a size square of size 3. Okay. So probably not a little unconventional, but I'm just going to make the square of what I've seen, like the max square. I'm just going to make it a default dict, just because I don't want to have to deal with the fact there's going to be negatives and stuff, and it's just annoying. So we'll go through each cell in the matrix. Okay. And then what are we going to do? We're going to... So the only way there can be a square in the cell is if the matrix at that cell exists. So if matrix Vij, so if this is even potentially a square, right? Then the size of the square at this cell, so S at this cell, Ij, is the minimum of what? Well, the left of me. So what's to the left of how many 1s are to the left of me, right? So basically the min of, right, when we were solving this square system here, right, the min of, well, how big is the square that I could create if I include what's to my left, right? So that's the left part. And then the minimum of this square that's above, that I can create with the leg, I guess we'll call it a leg, above me. Right? And then the size of the square that's diagonal to me plus 1, right? Because if it's a 3 by 3, then I can create a 4 by 4. And the size of the square that's above me. And then plus 1. Because I can create a square that's 1 bigger than that, right? Like if so the diagonal above me is a 2 by 2, that could provide me with a 3 by 3 if I have the right proportions. Right, if my left and above are correct. Okay. So let's take a look if that printed out the right thing. So let's say the problem is it's not going to look as nice. Whatever. Let's just print S. It's not going to look as nice because the default dict, so it's not going to be formatted like a grid. So just be forewarned. Okay, invalid syntax. If matrix of... What am I doing? If matrix of ij. Okay, so this is a little messy, but... So there's a size 3 square at 2, 3, right? So 0, 1, 2... 0, 1, 2, 3. That's right. Right, there's a size squared at 2, 2, a size 1 square at 1, a size 1, 3. So this looks right to me. Right, and I could always, like, add all these values to a matrix and then print it out, but I'm not going to do that. So then the answer, again, we said would just be the sum of the maximum squares at each cell. So we'll print these values. Let's run that. Okay. And then we pray that there's not something I'm not thinking about. Okay, cool. Wondering why my memory is so bad. I think my memory is good. For whatever reason, my memory is bad. Maybe because I'm using a default dict when I don't really actually need to, but I just didn't want to deal with the fact that we have negative considerations and, you know, Python when it's it doesn't matter. I just didn't want to add an additional conditional, so I didn't use a dict. So for this solution, what is the runtime and what's the time complexity and the space complexity? Okay. So it's an n by m matrix, right? So we'll call n, let's say that n equals the length of the matrix, right? And m equals the length of matrix 0. So we have to create three different systems that are going to contain information for each cell, right? So this is the size of the matrix, this is the size of the matrix, and then our default dict S will become the size of the matrix when it's done computing. So that means that in terms of space, right? And then we don't create anything else. So in terms of space, we have big O of n times m, right? And this is linear with the whole size of the matrix, right? Because these are just 2 dimensions of the matrix. So this is a linear algorithm. So don't let this could be confusing, like, oh, it's not linear. It is linear, right? It's just linear with respect to n times m. Okay. And then time complexity. Well, we have to go through the whole matrix once. So n times m. Then we have to go through the whole matrix again, another n times m. And then we have to go through the whole matrix a third time, another n times m. And then we have to sum all the values of the matrix n times m. So that's like 4 times n times m. But that doesn't scale. You know, that 4 is just a constant. It's not going to change independent of, it's going to be the same independent of how large our input it is. So that's 4 times n times m. That's just big O of m times m. All right. I'm kind of wondering if there's a constant space, but I don't think that's possible. It's probably just the fact that I'm using a default dict, which is giving us this memory usage. Not a big deal. You know, I didn't want to deal with the fact that things were negative, but I've already kind of articulated that point. All right, guys. Have a good one. If you're here, say what you think of my dog in the comments. What's up, G? My best friend, man. Peace out, guys.